Experimental versus theoretical probability. Today in class we looked at the difference between experimental and theoretical probabilities. And we discussed that theoretical probability is what should take place in theory. And we base what should take place in theory on the mathematical numbers for any given situation. So we want to look at our expected outcome divided by the total possible outcomes. Another way I could say that is the expected outcome divided by the total number of sample spaces. Problem number 1 asks us to find the probability, remember the P stands for probability, of whatever's taking place in the parentheses, or in the, So, the probability of a number greater than 4 on a number cube. In order for it to be greater than 4, it would have to be a 5, a 6, and those are the only two options, 5 and 6. So, my expected outcome, those qualifications which meet this statement are 5 and 6. There are two items that meet that statement. My sample space, remember, are the values 1, 2, 3, 4, 5, and 6, so 6 different values. This would then simplify to 1/3, which we would know equals 0.3 repeating, which would then be 33.3 repeating percent. Let's look at number 6, because number 6 has something different going on. We have this little apostrophe after the P. And so remember that the apostrophe tells me that we are looking for the complement. So we're looking for the probability of not getting a 5 on an 8-sided die. The probability of not getting a 5. Well, that means I could get a 1, 2, 3, 4, 6, 7, or an 8. So I would add up the number of values, 1, 2, 3, 4, 5, 6, 7 values would not be 5s over a sample space of 8 total values. And so now we will divide 7 by 8. And that would give us 0.875, which we know would equal 87.5%. Let's see, let's look at number 13 looks good. You have a deck of cards and you randomly draw one card. And so this was why I had you draw the deck of cards in Friday night's homework, is because within Friday night's homework you learned the various values of cards. And so I know that there are 52 cards in a deck. And our probability statement is asking, what is the probability of me getting a card lower than a 10? I could state that by saying probability of a card lower than 10. So I want to figure out what those solutions would be. Ace is lower than 10, 2, 3, 4, 5, 6, 7, 8, 9. That would be 1, 2, 3, 4, 5, 6, 7, 8, 9 numeric values. And we have to remember that each of these values would be present for hearts, diamonds, let's pretend to call that a club, and spades. So I'm going to have 9 times 4 different suits would be 36. And so now I'm going to simplify my fraction. Both numbers are divisible by 4. 36 divided by 4 equals 9. 52 divided by 4 equals 13. 9 divided by 13 would give me approximately 0.692, which is going to equal 69.2%. On the back side, your instructions are to roll a number cube 30 times and record the results in the chart. If you do not have a number cube, you can use the virtual die on either the website provided or on your own. So if I were to roll a number cube and I got a 6, oh, that's not a 6. Let's go ahead and say I rolled a 3 my first time. So I rolled a 3 and then I rolled a 6 and then I'm going to roll my die again. And I got another 3. And I got to roll my die again. And I got a 2. And for the sake of time, I'm going to go ahead and fill in the rest of my chart somewhat randomly. You would not be permitted to do this. So you could end up with data that looks something like this. Everyone's experiments are going to look slightly different because it's all luck of the draw, or in this case, luck of how you roll your die. And so after filling in my frequency chart, I could fill out the questions below, such as, what is the theoretical probability of rolling a 4? Remember, theoretical probability tells me that I'm dealing with what is the probability in theory. So it's based on the probability of my expected outcome. I have one solution that would be 4. Out of my total sample space, I have 6 values on a die. So 1 divided by 6 would equal 0.16 repeating, which equals 16.6 repeating percent. Then the question asks, what is the experimental probability of rolling a 4? Well, experimental probability is a totally different animal. Experimental is dependent upon the outcome of your particular experiment. So your solution could look quite different from mine. My solution has 1, 2, 3, 4, 5, 6, 7 rolls, gave me my expected outcome. And we already know that we did 30 rolls. So 7 out of my 30 rolls were a 4, which equals 0.23 repeating, which equals 23.3 repeating percent. This then gives me the ability to compare the two numbers. How do these numbers compare? Well, in this particular instance, my experimental probability was much higher than the theoretical probability. I'm going to let you give the rest of the questions an attempt on your own based on your own theoretical tallies, and we will discuss them tomorrow in class.